Chapter 7 deals with exponential models and logarithms. Our focus in this first section is just on the exponential models. We are going to look specifically at exponential growth and decay. All right, the types of equations we might see, the types of graphs we're going to see. Do you have a picture in your mind of an exponential growth curve? Anybody have an idea? What does it look like? All right, so it starts low and curves up. All right, exponential decay, opposite, starts high and goes down. Yes? But it's not a linear situation, right? Not a straight line. It says you can represent repeated multiplication with the function, with the form y equals a times b to the x power, where b is a positive number other than 1. An exponential function is a function with the general form y equals a times b to the x. We have this restriction that a cannot be 0. What would happen if a is 0? The whole thing becomes 0, yes? 0 times b to the x is going to be 0. If we just have the equation y equals 0, that's just a horizontal line, right? That's not growth or decay. So a can't be 0. Our other restriction, b has to be a positive number, something bigger than 0, and it can't be a 1. What would happen if it was a 1? What's 1 to the x power? 1. Doesn't matter what power I put in there, right? It's always going to be a 1. 1 times a is going to be a. We would get another horizontal line at y equals whatever a is. Okay? So in order for it to be exponential growth or decay, a can't be 0 and b can't be 1. In an exponential function, the base b is going to be a constant. It will be a number. Okay? It's the x that's up in that exponent position that's the independent variable. That's what's going to change. The domain are all real numbers. Our exponent can be fractions, decimals, positives, negatives, 0. Okay? It can be anything. So we're going to start looking at a couple graphs. The first one that we're going to graph is y equals 2 to the x power. You are going to be graphing these by hand. I know I told you needed a calculator today, but that's for the later part of the notes. Okay? So our first one, we're going a little bit more extensive than I would expect you to do on most questions. In other words, you don't need quite this large of a T-chart, but I want you to start to see patterns. Okay? So we're going to start at the bottom. We are taking 2 to a power. What do we get if we take 2 to the third power? We get an 8. What do we get if we take 2 to the second power? 4. 2 to the first power. 2 to the 0. 1. Yes, anything to the 0 is 1, right? What about 2 to the negative 1? Becomes 1/2. Why? It had to flip, right? We talked about the negative powers making it flip over. So this becomes a 1/2. 2 to the negative 2. It's going to flip over and get squared. 1/4. 2 to the negative 3. 1/8. And 2 to the negative 4. Now, can I graph 1/16? No. It's going to be too tiny to distinguish it between that and 1/8. However, I want you to see the pattern to know where those are headed. What would be 2 to the negative 5th? 1/32. 2 to the negative 6. 1/64, right? My number's getting smaller and smaller and smaller. Is it ever going to get to 0? No. It's always going to be 1 over something, yes? Okay. So when I go to plot them, I'm going to start with the easy ones. When x was 3, we were up at 8. When x is 2, we are at 4. When x was 1, our y value was 2. X being 0 gave us a y of 1. X being negative 1 gave us a y value of 1/2. Then we were at 1/4, 1/8, 1/16, etc. Okay? What I want to see on your paper when you graph these is that you indicate that you are getting closer and closer and closer to the x-axis, okay, on that side. So draw it in. You have a little more control over your pencil than I do with my goofy smartboard. So what's wrong with the way I graphed it? My graph, my line went under the x-axis, right? It shouldn't be doing that, okay? It should be going right above. Again, it's not oriented very well. It should be just right above that x-axis, okay? So on a test, I would ding you some points for that. You need to know that it's leveling off right above, okay? The one thing I don't want you to do in your trying to make sure you don't cross it, I don't want you to have it come and swing back up, okay? It doesn't come back up, it levels off. Okay. All right, next one. We are graphing y equals 2 times 3 to the x power. Again, let's start with the easy positive ones. If I plug a 3 in there for x, do I do 6 to the third? No, because exponents come before multiplication in our order of operations. So 3 cubed is 27. 27 times the 2. Okay? If I put a 2 in, 3 squared, 9 times 2. Okay? 3 to the first times 2. 3 to the 0 times 2. 3 to the negative 1 becomes 1/3 times 2 would give us 2/3. Okay? If I put a negative 2 in there, 3 to the negative 2 means it's going to have to flip over and it's going to get squared. What happens when I take a 1/3 and square it? 1/9 times that 2 would be 2/9. All right? Put a negative 3 in there. 1 over 27 times the 2, so 2 over 27, 2/27. Now, again, that's going to be really hard to graph, right? But I want you to see that it is getting closer and closer to 0. So we'll plot the ones that we can do on our graph. We'll skip the 54 and the 18 because they're too big. We could change the scale of our y-axis if we wanted, but we should still have enough points without doing that. So over 1 up 6, 0, 2, negative 1, we're at 2/3, then we're at 2/9, and again, you should be showing that you're getting closer to the x-axis. Do we have enough points to see our curve? All right, go ahead and draw it in. What happens when we take a fraction like this 1/3 to a power? If we start with the bottom again, what's 1/3 to the third power? 1/27. Okay. 1/3 to the second power? 1/9. 1/3 to the first power? 1/3. To the 0 power? To the negative 1. Yeah, it's going to flip it over. Now it's going to become a 3. A negative 2 is going to flip it over and square it. So we get 9. And a negative 3 is going to flip it over and cube it. Okay? So when you just have a b term to some power, notice the comparisons here. Right? A negative power is just going to flip over the other answer. Now, if we had an a value in there, that would adjust it a little bit. But without an a value, you should see that pattern. All right, plotting these points. 27 is too big, but we can graph negative 2 and 9, negative 1 and 3, 0, 1, 1, 1/3, and 2, 1/9. So what is this a picture of? Decay. This would be exponential decay.
Oh, decay.
Okay?
I'm thinking like literally the letters D-A-K.
Questions about that? All right. When we are graphing exponential functions, it helps to identify some criteria or characteristics of the graph. Helps to know where the y-intercept is. We should be able to tell the y-intercept from our equation. Also, an asymptote, we're going to talk about that. We should be able to identify domain and range, and we should be able to tell if it's growth or decay. And we can get all of that from the equation. We don't even have to have the picture. Have you heard the term asymptote before? All of you should say yes, because I just read it to you. How about before this year?
I don't remember where.
Okay. An asymptote's a line that your graph is approaching as you move far away from the origin. Okay? Students often get confused because they're looking near the origin and they're saying, but my graph isn't approaching that line. It's not what's happening near the origin. It's what's happening as your x value gets really big or really, really tiny in the negative direction. Does that make sense? So, if you go back and look at our graphs, the x-axis is the line my graph's approaching. As I move farther and farther from the origin, right, I'm getting closer and closer to that x-axis. So, for these examples, that would have been my horizontal asymptote. Okay? There are vertical asymptotes, but not for exponential curves. All right, they're always going to be a horizontal one. All right, and because it's a horizontal line, it's always going to be y equals something. So in those examples, what equation would we use for the x-axis? Y equals 0. Okay? Can you picture that ever changing? Can you picture an exponential growth curve that would have some other horizontal asymptote? Yeah, we've talked about transformations all year, right? If we shift this whole thing up or down, that asymptote moves with it. Okay? All right. The next piece is just kind of a summary of what we've been talking about. There is a little typo. This should have a little x up here as an exponent. So if you could fix that on yours. Should be y equals a times b to the x power. We said a can't be 0, b has to be positive, but not 1. The b is going to be a constant. It is not your variable in this case. It will be a number. The x will be our independent variable. Okay. For growth, we said b has to be a number bigger than 1. For decay, we are looking at something between 0 and 1. Now think back to the examples we just looked at. The last one we graphed was a 1/3 to the x power. So our b value was 1/3. That's a number between 0 and 1, and we got an exponential decay curve. Okay? Common mistake is for students to say, if b is a fraction, then it's decay. That is not the case, because I can write a fraction that's bigger than 1. If you say it has to be a fraction between 0 and 1, then that's valid. But just saying it's a fraction automatically makes it decay is not true. Okay? You could have a decimal number that's bigger than 1. Yes, that would be a growth curve. It won't be a decay curve. Yes, you will have b values that are fractions. You will have b values that are decimals. Okay? We talked about an asymptote. This next one says the y-intercept is 0, comma a. I want you to think about that for a minute. If we have the generic equation a times b to the x power, and I'm plugging in a 0 for x, what happens here? B to the 0 becomes 1. 1 times a is always going to get you a. That's why our y-intercept will be our a value. Okay, so you can see that right by looking at the equation. You don't need a graph of it. Our domain, we said, was all real numbers. Our exponent can be positive, negative. It can be decimals, fractions. It can be 0. Our range, it says y is greater than 0. Does that fit with the graphs that we just did? All of them were leveling off just right above the x-axis, right? They weren't touching the x-axis. So they are going to be greater than 0. Again, that would change if we do what? Shift it up or down, or if we reflect it over. Okay. So I'm going to pause the recording here. If you can answer all these questions just based on the equation, that's great. If you have to go back and look at the picture of it, you can. These are the 3 we just graphed. I want you to fill in this information. All right. So y-intercept. We said that's the value for y when x is 0, correct? So if you put a 0 in here, what happens? You get a 1. Now, this compared to this. Here, we have an obvious a value, right? We can see it. What's my a value over here? Nope, 2 is my b value, right? B to the x, what's my a value? A 1. We could do 1 times 2 to the x power, right? That's why our a value is 1. Okay? Asymptote. Y equals 0. Okay? Domain. All reals. Range. We are slightly above 0. Now be careful, because you guys have been in the habit of saying y is greater than or equal to 0. It's not equal to 0. It will never touch that asymptote. Growth or decay? This one was growth.
So with an asymptote, is it always that the thing will never touch the asymptote?
The asymptote is the line your graph approaches as you move far away. There are functions that cross a horizontal asymptote near the origin, but they approach it further out. Okay? So I can't say that you're never going to cross a horizontal asymptote because there are functions out there that do it. But exponential growth and decay curves won't touch it. Okay? Y-intercept on this next one. 0, 2, asymptote. Y equals 0. Domain. All reals, range. We're above 0. Growth or decay? Growth. What are we looking at in the equation to tell us if it's growth? Yeah. We need our b term, right? If b is bigger than 1, it grows. If it's between 0 and 1, it decays. So our next one is what kind? This one would be a decay. Y-intercept? 0, 1. Asymptote? 0. Domain? Range? All right. So we haven't gotten to any of the ones where we shift them. Yes? That's coming later. Something to look forward to. All right. I'm going to pause the recording again. This time I want you to go through these with your table mates and determine just 2 things. Is it growth or decay? And what is your y-intercept? All right. First one. Growth or decay? Growth or decay? Decay. There we go. And we're looking at this piece, right? That tells me it's a decay situation. What is my y-intercept?
12.
The 12. All right. Second one? Growth because of the 2. And y-intercept?
25.
All right. The last one here that I asked you to just identify those 2 things on. Written a little different. I didn't give you the equation yet, right? It says you put $1,000 into a college savings account for 4 years. the account pays 5% annual interest annually. Do you know what annual means? Yearly? Okay. Is it growth or decay? And a lot of kids say decay because you're looking at what? So 5% is written as 0.05, right? So you see that number and you think it's smaller than 1, right? It's going to decay. If you put money in an account and get interest, is your money going down? No. So it is not decay, it is growth. And here's why. Well, let's go back one sec. What's my y-intercept? Yes. Okay, so this is my A value, correct?
Yeah.
And we're going to start talking about how we create these equations. So I'm starting with $1,000, right? It's gaining interest. If I put in 0.05 here to some power, I'm losing money. That's saying I'm losing 95% of my money every year. That's not what's happening. I'm supposed to be getting an extra 5%. Yes? Yeah. It has to be 1.05 because I keep the original 100% of my money. That's the 1 part. And I'm getting an extra 5%. Does that make sense? So my money is being multiplied by 105%. Okay? The 100 keeps my original amount in there. The 5% is the extra I'm getting. Does that make sense? We're going to look at a slightly different version of that in just a minute. There are a couple terms that I want to clear up. It says, for exponential growth, y equals a times b to the x power, with b being greater than 1. The b is called our growth factor. Okay? B is the growth factor. A quantity that exhibits exponential growth increases by a constant percentage each time period. So when they talk about population growth or interest for money, all right, that's going up by a certain percent. That percentage of increase is our R value. It is written as a decimal, and it's called the rate of increase or growth rate. So in that last example where we had 1.05, the 0.05 was the growth rate. Our B value was 1.05. It's always going to be 1 plus R. Okay? For exponential decay, it's just the opposite stuff. B is now called the decay factor. It's something between 0 and 1. The quantity is decreasing by a set percentage each time period. That percent that it's going down is your R value, which is called your rate of decay. For decay, the R value is usually written as a negative value. Okay? So, most of the time, you will still see it listed as 1 plus R, but your R value is going to be a negative number. So 1 plus a negative number is going to be something smaller than 1. Does that make sense? We'll look at some examples of that. All right. The next formula should look very similar to the one we just were talking about with our money. This A here is our initial amount. Okay, that was that $1,000 that we had in that example. R is your percent, your rate of growth or decay. In our example, we were growing 5% with our interest. So our R value would have been 0.05. Okay. The 1 is in there, remember, to keep the original 100%. This is our final amount, and T here is the time. Usually that is in years, but it doesn't have to be. There's interest that can be compounded monthly, things like that. All right. All right, so we invest $1,000 again in an account at the end of 6th grade. The account is going to pay 5% annual interest. We want to know how much money will be in the account after 6 years. And I'm going to stop you before we even get started on this, because the most common thing students do is they want to dump all the numbers in and just get a final number. Most of the time, it is going to ask you to write a model first. That means write a generic formula that's going to work, and then use that formula for a specific time. Okay? So we're going to start out with what our variables should be. And is this a situation that involves exponential growth or decay? What in the word problem leads me to know that this should be exponential? What? Annual interest typically is exponential, yes. But I want to be more specific. What do you see in there that's telling you that? Okay. It has to increase by a fixed percent. All right, for it to be growth or decay, increase or decrease by a fixed percent. So that 5% increase is what's telling me it's going to be exponential growth. We want to decide what our variables are, and we're going to write our model. So we can use X and Y. We can use A, capital A for final amount, and T for time. Doesn't matter to me. I'm going to go ahead and use A for final amount. And I'm going to use T for time. In this case, what kind of time frame are we looking at? I should say, what kind of unit for time are we looking at?
Years.
Years, yep. Now, we've decided on our variables. We're going to write our model. This is generic. It doesn't use a specific time. Okay? So, our final amount. We start with our starting amount, $1,000. And how is that money changing? It's increasing by, be careful, it's increasing by what percent? It's increasing by 5%. Yes? That is my growth rate. It's a 5% increase. What goes in parentheses is 1 plus that R value. Does that make sense? And I'm fine with you writing that right away as just 1.05 without the plus sign in there, but I need you to understand that it's 5% increase. That's your growth rate. And then we're raising it to a T power for time. Now we can use that to solve it. And you said we wanted how many years? 6 years. So grab your calculators. Type in 1,000 times 1.05 to the 6th power. What do we end up with? $1,340.10. All right. This time it says we're starting with $1,000. We're going to get 5% annual interest if we make no additional deposits or withdrawals. And I stated that because if you take money out or add extra money in, it's a different formula. Okay? For how many years will it take the account to grow to at least $1,500? How is this different? We know what we want to get to. We want $1,500. We just don't know how long it's going to take us. So my equation, it's the same equation I had before, right? But we want our amount to be $1,500. Now, I can plug a $1,500 in there for A. The problem is we don't know how to solve that yet. You will learn how to solve that later in the chapter, but for right now, we don't know how to solve for an exponent. Okay? So how are we going to get around this? We're going to use your calculators. Go to your y equals screen. Clear out any equations that you have in there, and make sure any of your stat plots are turned off. So all that plot 1, 2, 3 at the top should be unhighlighted. We're going to enter two equations. The first one is our generic model. The second one is the specific y value that we want. Okay? Thank you. Come on, my 0 key doesn't seem to want to work here. All right, and the second one, 1500. Okay, now, if we were to hit graph right now, you probably wouldn't see anything. Because we're looking for a y value of 1500, and if our graph only goes up to 10, we're not going to see it. We have to change the window. So go to your window key. I'm going to set mine to be from 0 to 10 for x. That means I'm going to look and see if this happens within the first 10 years. Okay? If I don't see it happening, I can always make that bigger. My y values, I set from 0 to 2000. That gets me beyond that 1500 value that I'm looking for, right? The other thing to notice, my y scale here, I set at 0. Otherwise, it's trying to put 2000 tick marks in that little window, and it's just going to look like a really thick line. You don't need the tick marks in there, okay? All right, so then we're going to hit graph. So the blue curve is my y equals 1000 times 1.05 to the x power, right? It's a very gradual exponential growth. 5% increase isn't changing much, okay? The horizontal red line is my y equals 1500. Do they cross?
Yes.
Okay, so I know that I'm going to reach 1500 within that window of 0 to 10 years. I could do an intersection. So second trace, number 5, enter, 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 and it's showing me here that it intersects at an x being 8.3. The problem is I can't give an answer of 8.3 years because it's annual interest. I'm only going to get it at the end of each year. Does that make sense? So I want you to go to your table, so second graph, and look at your table. The red one here is just that horizontal line at 1500, so my y value is always 1500. Looking at the blue one, that's my curve. Do you see that somewhere between years 8 and 9, I hit a 1500 level? Does that make sense? So to answer their question, after how many years will I have at least $1,500, I would have to round it up to, say, 9 years. Does that make sense? Even though I'm going a little bit above the 1,500, I'm not going to reach it at 8 years. So at 8 years, we were at 1477.5, and at 9 years, we were at 1551.3. So I would say after 9 years. Okay? Now, did I actually have to graph it to figure that out? If I've got my equations in there, I can go right to the table and look for the values. The graph just gives me a visual of where to look, all right, about what year should I be looking for. Okay? All right. The graph that we just looked at was technically wrong because this is what we call a discrete situation. Since we can't gain interest in the middle of a year, we really wouldn't have a full curve. We would have exact little dots like you see here. How much money do I have after the first year? How much money do I have after the second year? But we always fall back on just a smooth curve. It's kind of assumed that we know in this context, we're really looking at specific dots at the end of each year. Okay? If I know that something fits an exponential curve, and I'm given two consecutive values, meaning the y value at 2 consecutive years, I can figure out the rate of growth. Okay? To do that, our rate of growth would be to take y2 minus y1 and divide it by y1. Okay? So take your second y value, the y value at the second year, minus the y value from the first year, and divide it by the y value of the first year. Okay? And once I know r, I can dump it in and figure out what my b value should be. Okay? All right, so our last question, we're going to look at that. It says the table shows the world population of the Iberian lynx in 2003 and 2004. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will there be in 2014? First thing we're going to do is define our variables. Okay? I'm going to let x equal the number of years since 2003. What that allows me to do is to think of 2003 as times 0, my starting amount. Does that make sense? And then 2004 would be my first year. Okay? Y is going to be the population of the lynx. All right, so we want to determine the rate of decay that's happening. Our R value is going to take the second Y minus the first Y and compare it to the first Y. Okay? Y2 minus Y1 divided by Y1. So 120 minus 150 divided by 150. We're looking for the change that's happening. Okay? 120 minus 150 gets me negative 30. What's negative 30 divided by 150? Okay. So we had said earlier, remember that R, when it's decay, is going to end up being a negative value? All right. Our B term is just 1 plus R. So 1 plus a negative 0.2 is what? 1 minus 0.2. All right. So when I go to write my model, how many links were there at the start? $150. All right. Oops. We had 150 at the start. We are multiplying by what? 0.8. We found our b value to be 0.8 to the x power. Okay? And again, if you want to use t for time, that's fine. Then it says, use your model to find the population in 2014. Well, we defined x to be the years since 2003. So how many years later would that be? Compare that to 2003. 11 years. So we want our x value to be 11. So grab your calculators. 150 times 0.8 to the 11th power. Now, if you get a decimal, are you going to give me a big, long decimal answer here? Why not? You can't have half a lynx. All right, so rounding it, we'd get what? About 13? All right. What if I wanted the population in the year 2020? Yep. What's 2020 minus 2003? 17. So we're going to change our time to 17. What do we end up with? About 3. Now think about that. In the year 2003, we had 150 links. Next year, we're going to have 3. Okay? Maybe. The trend may have not continued that in that same fashion. I want you to look at this, the 0.8. Does it make sense that if we are losing 20% of our population, right, the negative 0.2 means it was going down 20%? Does it make sense that we're keeping the other 80%? Okay, so when you think about setting up your formulas, this is what stays, right? Not what's going away. We're getting to keep 80% every year. Okay? All right, there's your assignment. I will get you guys some graph paper.